I am excited to introduce our first speaker, Harini Suresh, who will be presenting a framework of potential sources of harm through the machine learning lifecycle.
So hi, everyone. My name is Harini. I'm going to be talking about a framework for understanding sources of harm throughout the machine learning lifecycle. So as you probably know, there have been a lot of high-profile cases of machine learning-based systems in the wild causing harm. For example, publicly available facial analysis technologies that performed worse on darker-skinned women, or a case where an incorrect facial recognition match led to an innocent person being arrested. But it's not just facial recognition. These issues recur across domains. In healthcare, for example, using the cost of care as a proxy for illness led to a widely used algorithm for estimating patient risk to deprioritize Black patients. These instances were reported about in fairly high-profile ways, but they aren't uncommon. In Virginia Eubank's book, Automating Inequality, she investigates automated decision-making systems widespread in government programs and social services, showing how they disproportionately punish poor and working-class people. And even beyond outcomes that are clearly harmful, there can be more insidious consequences of machine learning systems, like upholding damaging stereotypes. This is an older example from Google Translate that replicates gendered stereotypes about doctors and nurses. And in her book, Safia Noble delves deeper into the ways that search engines and advertising recreate a culture of racism and sexism. This talk is not only going to be a laundry list of all the ways that machine learning systems screw us over. There are certain moments of promise. For example, the researchers who investigated racial bias in the healthcare algorithm worked with its manufacturer to come up with a better, less biased proxy for illness that they then used to retrain the system. And the reason they could do this is because they were able to identify that healthcare costs were a historically biased proxy because of structural inequalities in access to care. This comes from an understanding of the data generation process for this particular application. The same solution couldn't just be ported over to the facial recognition case or the search engine example. It wouldn't help there. So the question then is, how can we understand and identify the sources of harm for a particular application? We noticed that a lot of popular rhetoric to this end isn't useful for doing that analysis. For example, a fairly common refrain is that models are biased because data is biased. And it's not necessarily that this statement is false, but it's not helpful because it treats data as a static artifact divorced from the process that produced it. This process is long and complex, grounded in historical context, and driven by human choices and norms. Understanding the implications of each stage in the data generation process can reveal more direct and meaningful ways to prevent and address harmful downstream consequences that overly broad terms like biased data can mask. And it's also important to acknowledge that not all problems can be blamed on the data. The machine learning pipeline involves a lot of other choices, from model definition to what to optimize to the way that the system is integrated into a real-world setting, each of which has important implications. So the goal of our framework is to provide a structure and vocabulary for understanding distinct sources of harm throughout the entire data generation and machine learning lifecycle. The goal is to facilitate a more methodological analysis of the risks of a particular system and to inform mitigation techniques that stem from an application-grounded understanding of data generation and development processes. Importantly, understanding where intervention is necessary and how feasible it is can also inform discussions around when harm can be mitigated versus when it's better to not deploy a system at all. Thinking prospectively for new systems, we hope that the framework can help developers or designers anticipate these issues and prospectively design more thoughtful and contextual methods for data collection, development, evaluation, and deployment. And for external stakeholders as well, we think that an understanding of how and why issues arise can provide a valuable guide for asking the right questions to probe or push back on a system. So now I want to walk through the different sources of harm in our framework. Because we wanted to focus on sources, these were defined and organized around the different stages of the machine learning lifecycle. Each issue kind of maps to one of the processes in this figure. Another quick note is the use of the word bias, which we mainly use because of precedence. And in our case, these biases refer to distinct sources of harm, and you can think about them as breaking down more vague terms like data bias or algorithmic bias into more useful and granular concepts. And so I'll briefly define each and give an example. Before any sampling, measurement, or modeling happens, there's the world from which all data is collected, including all of its historical and social contexts and systems of oppression. Even if we sample and measure carefully and correctly, And even if our data accurately reflects the state of the world, it can still inflict harm. We call this historical bias. For example, word embeddings are learned vector representations of language that encode semantic meaning and are the basis for a wide range of NLP tasks like translation or speech recognition. Studies have found that word embeddings, which are trained on giant collections of text from websites, Google News, Wikipedia, et cetera, reflect real-world biases at the time. So the plots shown here, for example, are from a paper showing that embeddings for certain occupations are highly associated with words that represent different genders. And in particular, the strength of the association is correlated with the actual gender disparity in those occupations over time. So these embeddings accurately reflect structural inequalities and stereotypes in the world, but these are things we want to overcome, not encode and reinforce. Representation bias then arises when defining a target population or when sampling from it, and is ultimately due to underrepresentation leading to worse generalization for certain people or groups. For example, ImageNet is an extremely commonly used dataset for computer vision tasks and pre-trained models. It's intended to be widely applicable, but certain geographies are very underrepresented. The vast majority of images come from North America or Western Europe, and only about 3% come from China and India. This paper showed that a classifier trained on ImageNet fails to generalize well for certain classes like bridegroom when the images come from undersampled countries such as Pakistan or India. Measurement bias can then arise when actually defining and measuring data from that sample. In order to encode complex concepts into measurable data, we necessarily have to create simplistic proxies and categorization schemes. We run into problems when these proxies are too simplistic, misguided, or are measured incorrectly or differently across groups. For example, risk assessment tools for pretrial decision-making attempt to measure some underlying notion of riskiness. This is clearly an abstract and unobservable concept and is arguably an unfounded attribute to even assign someone. In an attempt to operationalize riskiness, Northpoint's Compass tool used proxies like whether or not friends or acquaintances have been arrested or served time. That's part of the survey they administer shown on the right. There are many reasons why this proxy is problematic, only one of which is that because minority communities are more highly policed, it's differentially mismeasured across different groups. And the resulting model had a significantly higher false positive rate for Black defendants versus white defendants. So then aggregation bias arises during model definition, when a one-size-fits-all model is applied to data where examples are actually more heterogeneous, reflecting, for instance, differences in cultures or norms. So shown here is a project that analyzed Twitter posts of gang-involved youth in Chicago. By hiring domain experts from the community to interpret and annotate tweets, the researchers demonstrate the context-specific meaning of certain hashtags, phrases, or references. So for example, words that might appear to convey aggression in a general context might actually be lyrics from a local rapper in this specific context. Ignoring this group-specific context in favor of a single, more general model built for all social media data would likely lead to harmful misclassifications of the tweets from this particular population. So then there's the actual model optimization. Learning bias arises when the choices involved here, like the choice of objective function, cause downstream harm, like amplifying performance disparities. For example, recent work found that differentially private training can lead to a model that performs worse on underrepresented data. And a similar study found that using methods like pruning to compress models during development has a similar effect, learning to preserve information about the most frequent features and subsequently being worse for the less represented ones. After training, evaluation bias arises from issues with the benchmark data or the metrics that are used to measure performance. A few people have commented that this seems similar to representation bias, and it's true that they might both manifest as underrepresentative data sets, in one case used for training and in the other for evaluation. But I think about the impact of evaluation bias operating at a broader scale, influencing research directions and the types of models that are developed and deployed. I particularly like this quote from a recent paper that frames data sets as infrastructure. They say benchmark data sets that are recognized as go-to standards for evaluation and comparison often take on an authoritative role, and improvements on performance metrics associated with the benchmark become synonymous with progress in the subfield. Data sets that have achieved such authoritative status also play a unique and powerful role in structuring research agendas and values within machine learning subfields. And I would add that even the norm of easily benchmarking models against each other to evaluate them encourages reducing performance to a single number and doesn't create incentives for more complex subgroup analyses or more application-grounded evaluations. Yeah, and in their paper, Gender Shades, Joy Buolamwini and Timmy Gebru point out the drastically worse performance of commercial facial analysis algorithms on images of dark-skinned women. And while representation bias is certainly one source of the issue, standard benchmarks in the field, which are broken down on the right, failed to discover and penalize underperformance on intersectional subgroups, which shaped the development process that led to those deployed models even being considered state-of-the-art. The right benchmarks and evaluation methods should have penalized those models and helped encourage data collection or different models that specifically combated those errors. So after development, a system is actually deployed in a real-world setting. And deployment bias arises when there's a misalignment between the task a model was intended to solve and the way that it's actually used. This often happens when a system is built and evaluated as if it were fully autonomous, but in reality, it's embedded in a complicated socio-technical system with organizational structures and human intermediaries. The paper quoted here studied risk assessment tools deployed in Kentucky's criminal justice system, describing off-label uses of the tools for sentencing decisions, potentially increasing incarceration on the basis of personal characteristics. So an important takeaway from this is that identifying and addressing sources of harm comes from a context-specific understanding of a particular application. And a related takeaway is that different sources of harm necessitate different interventions. For example, measurement bias wouldn't be solved by collecting more data, since that data then still goes through the same flawed measurement process. But targeted data collection might be useful for combating representation bias. On the other hand, since measurement bias is an issue with the way that features and labels are produced, it may be avoided by using more thoughtful and context-aware annotation processes. Other mitigations might target the model. For example, since aggregation bias is an issue with the model definition, we might try to prevent it by choosing a parameterization that takes into account underlying differences in the data, like a multitask model. And evaluation bias might be targeted through collecting more diverse representative benchmarks, or through reporting more detailed metrics or more application-specific notions of success. Deployment bias is an issue with the real-world scaffolding around a system and could be targeted, for example, through intuitive interfaces for users to interact with the model and understand its limitations, or through education and training for users as to how the system should and should not be used. I mentioned these ideas very quickly and generally, but we have a more detailed formalization in the paper as well. And of course, these are just example mitigations that I'm putting out there, in part to illustrate that each is addressing a different underlying source of harm and is making assumptions also about which sources of harm are present and which are not. But there's not an easy checklist of solutions for each problem. The framework is more intended to provide a useful conceptual model for thinking through potential problems, understanding if and what mitigation techniques are appropriate, or for motivating new ones. So just some final takeaways. The machine learning lifecycle is long and complex. It extends all the way from historical context to integration into a real world setting, and there are important choices being made all throughout. And identifying sources of harm requires knowledge of an application and engagement with its stakeholders. And finally, techniques to avoid or mitigate harm are not one size fits all, and they should be targeted and context specific. So thank you. And feel free to reach out with any questions, or I can answer some questions now if we have time.
Thank you for a fantastic talk. If there are any questions, please type them in the chat or the Q&A. In the meantime, if there are no questions from the audience yet, I do have a question. I was wondering if you could comment on the interrelatedness that may exist between some of these sources of bias and how we should go about thinking about them in practice where systems are dynamic.
Yeah, that's a great point. One example of this that I was thinking about is learning bias. So a lot of the studies that sort of quantify how like differentially private training or compressed models create harm is through like amplifying disparities on underrepresented groups, which is related to representation bias. So I guess I don't have a general answer, but I think pinpointing places where there's like an upstream source can also help determine appropriate mitigation. So learning bias might not just be addressed by changing the objective function. We might leave the objective function as it is, but instead choose to like address the even more upstream harm, which is, or the even more upstream source, which is representation bias. But yeah, I think there's still more to do to like characterize that for a particular application. And I think it's probably application specific. And it's maybe more of an issue with the more downstream sources of harm.